Thank you for joining today. I'm Ric Gillams and I work in the Faculty of Engineering and Physical Sciences at the University of Southampton. And today I'd like to tell you a bit about a project I've been involved in for the last 3 months or so, which has been highly linked to the COVID pandemic and about how we can provide personal protective equipment, or PPE, for healthcare workers in the hospital. So in early March, as the pandemic was sort of picking up in London, one of the consultants in Southampton, Paul Elkington, was talking to some of his colleagues up in London, where the pandemic was that little bit further advanced, and it was becoming really apparent that the healthcare workers in the hospital were really struggling to deal with the volume of patients coming through. And one of the big issues around this was how to protect the healthcare workers, to stop them from becoming infected and then infecting uninfected patients, and also not being available to help people during this time. And so with the traditional masks, as we're all becoming acquainted with for going on public transport now and into shops, you have to be very careful about how you deal with that mask, because if you imagine that you've been on a ward filled with COVID patients, there's going to be a huge amount of particulate matter in the air containing the virus. And so if you then have a mask on your face and you're breathing through it, that mask might be able to stop the droplets of saliva that contain the virus. But then that piece of fabric across your face is then highly contaminated, and you need to be very careful about how you handle that to ensure that when you take it off, you don't actually end up contaminating your own face. And these masks they're pretty uncomfortable and very hot. I mean, for most of us, we only experience wearing them for half an hour to go to the shop or something like this. The more uncomfortable they are, the more inclined you are to adjust them or to fiddle with them. And so the challenge that Paul presented to us was, he said, is it possible to make something that just covers the whole head? So he said it'd be better if it covers the whole head, and then if you have a clear window through the middle, it will make it much easier to communicate with patients, because a lot of communication is non-verbal, especially with patients that may be hard of hearing. And so being able to see someone's face when you're talking to them, and especially in these difficult circumstances where you might be delivering bad news or trying to keep someone up to date with how they're progressing, it can be really important to be able to communicate well in that setting. And so the challenge was, is there a way that we can provide fresh, clean air into a kind of hood? And so we started sort of mocking up prototypes just over in the engineering department. So we started with things like this. So the kind of design criteria were things like you needed something that was water resistant, that could easily be cleaned. So in this case, we've used this membrane that you'd put underneath roof tiles. It's not the most beautiful looking thing, but it does the job. And then just a clear piece of plastic, and you'll see that actually in this case it's held in with duct tape. We bought a sewing machine from Hobbycraft and got going with trying to learn how to stitch. And it's fairly rudimentary, but it actually does the job pretty well. And in terms of its ability to be cleaned, we tried just putting one of these in a bucket of bleach, and I think it was in there in the end for about 3 weeks, and it was actually completely fine. But eventually we enlisted the help of a sail company called Kemp Sails, and they actually started producing these much nicer looking items. And so this one's got a sort of drawstring around the neck, so you can kind of adjust it to fit. And so this obviously looks a little bit more like it belongs in a hospital than our Darth Vader sort of top. And then the question was, how do you actually provide air into that hood? And so you don't really want just a jet of air just going straight down the middle of someone's nose. What you really like is just a kind of sheet of air that just kind of comes across the face. And so we got to work with a 3D printer. And I mean, yeah, 3D printers have kind of changed the way that we do sort of rapid prototyping and this sort of thing. So that we could very easily just take, so the sort of hoses we're using often have a sort of screw thread, because they're often reinforced to stop them from being squashed and so they can't become kinked and stop the airflow. And so a lot of them have these sort of spirals around the outside for this reinforcement, and so you can use that screw thread. So you just make the opposite screw thread in the 3D printer, and the hose just connects in. And then we thought we could take something like a sort of face shield. So you often have these kind of hoods, sort of like headpieces that you might wear in a workshop or something. And so we thought, well, actually, if you could just slot this diffuser onto the headband, then it would just sit there and provide this nice smooth flow of air across the face. So that gives you something of this sort of nature. And then you can attach the plastic screen. So that these visors actually came with a plastic screen on them, and so we were also incorporating our fabric hoods into that setup as well. And then you've got the hose that will deliver the air into the hood. We did wonder whether it's possible to actually have the full filtering unit on the head top itself, but for various reasons, including trying to get a long duration of use. So we wanted these to be suitable for doctors to wear, say on a shift of say 8 hours or so. For the healthcare workers in the hospital, you're often there for very long periods of time, and so you don't just want something that you have to change every couple of hours. And so, for that reason, we'd end up with like quite a bulky setup in terms of the filter, the fan, and the batteries to power it. And so it wasn't really feasible to have that weight on the head, and instead we moved it then down into either sort of a backpack sort of setup or onto a waistband. To develop from there, we started working with McLaren Formula 1 race team. Yeah, actually one of the highlights of the project for me was driving up the M3 to go and meet the head of chassis design from McLaren Formula 1 Racing to pick up a load of 3D printed parts that they'd actually made in the McLaren workshops. And so this was one of the designs that they came up with. So they sort of said, well, okay, I mean, they're very used to wondering about how air flows around certain spaces and things like this. And they just said, well, actually, you don't need to have a very big diffuser. You could simply just have an ellipse and then just squeeze the hose as it comes through, and it's just like a garden hose. And as you squeeze it, the water just sort of fans out. And so that obviously saves a lot of weight and a lot of time. If you think about printing that great big diffuser unit compared to printing something like this, it's much quicker. And then this headband would just sit on the forehead like that. So it sort of supports the hose and provides a mount for the hood all in kind of one go. So it was very interesting to see how those guys worked when they're much more focused on the actual manufacture side of things. So often in the university we kind of get carried away with coming up with these very complicated solutions to different problems, but we're maybe a little bit further removed from actually delivering those products onto a production line. And so it was very interesting to talk to those guys and see how their minds worked around the problem solving and minimising the amount of material that was involved. So I guess they're normally trying to save weight for their race cars, but in this case we also wanted to be able to produce these things very quickly. We also talked with them about whether we could make some slightly fancier connectors. So originally we just had these little plug-in connectors for the fan, and again it's just the screw thread up the inside, and then it just clips, just a push fit into the fan housing. And so then we talked about having this kind of screw, kind of quick release setting. So you can imagine a situation where you'd have the base units being held in the hospital and being recharged in a communal hub, and then individual users would come with their hood and their hose, and then they just want to be able to quickly just switch in and switch out and connect to a new base unit. So a lot of these kind of design features and things were just things that we came up with through these discussions with McLaren. So then moving on to kind of the core of the actual pack itself. So this is where all the kind of cleaning of the air is going to happen. And basically what we ended up doing was, in the first instance, I just got sent into town to see if I could find some Hepa filters. And it turns out these high efficiency particulate filters, they're often found in hoovers, they're often found in things like the extractors above cookers and things like this. And actually it's the same kind of filter material. And it's kind of pleated, so you get a high surface area, and there's things like static effects that encourage particles to just to grip onto the surface. And so anyway, these filters are very, very efficient. And so they're actually suitable for removing the sort of size of particle that you'd be interested in for COVID, which is not actually just the virus itself, which would be incredibly small, but it's actually the virus is often transmitted in droplets of saliva. So if you imagine someone talking or coughing, you're not actually talking about an individual virus floating through the air, you're actually talking about these droplets, which will then actually stick onto the surface of these filters. So taking these kind of Hoover filters, we then wanted something that could blow a significant volume of air into the hoods. So I was quite surprised when you start looking into these things. But basically, you end up wanting to blow around 150 litres of air a minute through one of these hoods, which I found quite astonishing. It's beneficial to have these kind of flow rates, because then if you've got this continuous stream of air coming out of the bottom of the hood, then if they're leaning over a patient and that patient coughs or sneezes, you're going to have this sort of force of air coming upwards, and so you need that kind of continuous flow just to kind of wash everything out and just keep the fresh air flowing and keep the contaminated air away from the healthcare workers' faces. And in order to get these big flow rates, I mean, you can get much smaller fans than this, of course, but actually what we found was if you use a really small fan, you have to operate it at very high speed, and so then they become fairly inefficient, but then also the noise they make when they're running is much higher pitched. So the bigger the fan, the lower speed you can use to generate the same airflow. In the end, we settled on a fan of this sort of size, and having gone for a fan of this size and sort of using these readily available sort of Hoover filters to go over the air inlet, then you're starting to look at something that, yeah, I think you'd agree with this, and then solving that into a battery pack and things. You can't really just mount that on the side of someone's head. That led us to look to different ways of supporting this kind of unit, and so we came across these bum bags, which are made for marathon runners, and so they've got these sort of hydration pouches, and so we thought, well, actually that would work quite well. We could modify that to fit our filter and fan into the middle, stick the battery pack in the side, and we've got something we can very readily modify. We, of course, cut them apart and tape them up with some duct tape, and then you end up with this kind of assembly mounted in here. And so this is very crude. This is one of the first ones that we developed, and so it's literally just a pack of batteries. Again, bit of duct tape just to keep the whole thing together. Just very rudimentary. It's just a simple switch, and then you can hear the fan starting up. And what's happening here is it's drawing the air in through the filter here, and then gets sucked up and blown out of the top here. And so that's where we can connect to one of these connectors that goes up to the hose to feed the air into the hood. I think it was less than a week from Paul sending over these sort of initial sketches he'd done on the back of an envelope over to my boss, and then we had a sort of very early version ready to go, and ended up driving it across town over to the hospital, and I ended up meeting the chief medical officer in the car park. And he said, "You must be Rick, I need that." And just took it off me, and I was, okay, I guess that was the right guy. But so it's a really bizarre way to do, I guess, research and engineering, but it's been a great opportunity to work with quite a diverse group of people, and to look into how we can solve all these problems. And having presented it to the board at the hospital, they then wanted to run some tests, and so I then spent another sleepless night making 5 prototypes to take them up to the hospital, and then we had a mixture of doctors and nurses who wore them out on the ward, and gave us feedback about comfort, whether they preferred a sort of backpack harness or just the sort of belt band, and talked about sort of different ways of sealing the bottom of the hood, different materials for the hood and for the screen as well, and we got some really positive feedback from there. And so then it was a case of identifying a company that was willing to take on this mad project and deliver thousands of items to the hospital in a very short period of time. Fortunately, Indo Lighting in Southampton stepped up to the plate, and then we worked with them, and it was nice to see that their work ethic was the same as ours, and so we had lots of emails going back and forwards at 2 or 3 o'clock in the morning, and have a few hours sleep, and then you'd be on video call trying to bottom out some of the different parameters, why we'd chosen different parts that we'd chosen, because we'd spent kind of, I guess at this stage maybe 2 or 3 weeks with a team of about 9 of us working pretty much around the clock, and everyone investigating different aspects of the problem. So to try and then transfer that information into the company in order to get them to get the best version of it that they could generate it in the quickest possible time was another interesting and fun challenge. Anyway, enough from me. Thank you very much for your time.